Hello everyone. In this video I'll give you a quick tutorial on a few points in RS2 that should help you with your lab this week. We're going to talk about converting the excavation boundary from a stage boundary to an excavation boundary. We're going to talk about adding a joint network and modifying those geometry properties, changing the joint mechanical properties, increasing the GSI in the material, and lastly I'll show you some ways to interpret the results using query boundaries. So let's get started. We have our model here. We've got our external boundaries very far away from our excavations. If we zoom in onto the excavations, you'll see I have the model set up fairly similarly to the current lab you're working on with the twin caverns. There are multiple stages set up, and I'll tab through those now. Stage 1 is in situ conditions, to make sure our model inputs are working properly. Next, we excavate, add the induced loads at 0.3 or 30%. We remove those and add bolts, and you may also add liners. And then we continue to stage through the excavation of these caverns for a total of 7 stages. In your lab, of course, you will have more stages and slightly different designs. So the first step is converting the boundary. You'll notice if you use the Add Tunnel Boundary option, it will create the excavation as a stage boundary. So I suggest right-clicking on that boundary, go to Convert Boundary, and change it to an excavation boundary. This simply matches the convention for modeling, and do the same thing with both. The next step is to add a joint network. You want to make sure to be in stage 1 when you're adding the joint network. And we go up to click on Add Joint Network. And we need to select all of the regions in the model where the joint network should apply, so everywhere. And so that's inside and outside all of our excavations and all of our stages. You can zoom out to just double check that it goes all the way through the model, and then press Enter. To help minimize computational time and effort for this lab, you will be simulating a relatively large spacing, so at least 5 meters. If the computation time is very long, you can even increase it to 8 meters, and just to see what it looks like. So we want 2 joint networks at dipping 45 degrees in the opposite direction. The first joint network is here. To add another joint network, we check on Use Multiple Joint Sets, and then click Add. In joint set 2, we want to have the inclination at minus 45 degrees, and so now you can see how that is updating in the model. The spacing I'll increase here as well to 8 meters to reduce that computation time. For this lab, we will be using parallel deterministic joints, and there are others you will potentially use in the future with different geometries. An important point is under this joint end condition, we need to change it from all closed to open at boundary contacts. And the top one is open at surface contact. That is assuming the top external boundary of our model is actually the ground surface. In this example, where we're several hundred meters underground, this is not the case. So we want to uncheck that, so it's not considered a surface contact at the top external boundary. At the external contact, we don't really want the joints to be moving, and as they are supposed to be set far enough away to reflect in situ conditions that will not be impacted by deformations in the excavations. So we'll leave that at no. We want the joints to be open at the excavation contacts to allow blocks of rock to slide or fall into the excavations if they will do that. So we keep that as yes. At material contacts, as we know in reality, joints can continue through different lithologies, and so in that case, and we will want to check that as yes. For open at the stage contact, the joints don't care where our excavation stages are. They will appear at that contact, so we want them to be open as well at that stage contact. Make sure you change this joint end condition in both joint set 1 and joint set 2, so I'll do that quickly here. Great, now we're all set. Click OK, and our joint network has applied. Once that's been done, you can tab through the stages and you'll see that the joints appear in all of the stages, which is perfect. Next up, we can change the joint mechanical properties. So we go up to Properties, into Define Joints, and in this case we'll use the same joint for both sets. First step in most modeling that you'll be doing is to turn off initial joint deformation. In this case, just use the default normal and shear stiffness values. We want to insert a slip criterion. You may use more Coulomb or Barton-Bandis, depending on where you find information in the literature. And then you want to turn on residual strength, so you have peak and residual strength. So I've entered some strength properties here that are reasonable for joints, but of course you'll be finding your own. So click OK. And now we want to change the material properties with this GSI value. If we go into our material properties, we have materials 1 and 2 are used in our model. If we go to strength, I've inserted some GSI values at random, and this was when we were modeling the rock mass as a homogeneous continuum where the joints themselves were included in GSI. Because we're now modeling joints explicitly in the model, we need to increase GSI so the rock mass strength is not over-penalized by double counting the weakening effect of the joints. So we simply need to increase the GSI value by about 10 points. And so we'll go up to 75 for peak, 65 for residual. And I'll be sure to do the same thing with the second material as well to increase it about 10 points. The reason the GSI value is not being increased all the way to 100 is because for computational efficiency we have joints that are being modeled explicitly potentially wider than they are in reality. So the GSI value that's still being used, that's less than 100, is accounting for some joints that we're not explicitly modeling. Great. So now we've set the material properties. We can save our model and we can insert our mesh. Now that we have joint networks in the model, we have an extra step in meshing to clean the joint network geometry. So we should go ahead and clean that geometry. Using these defaults are fine. These joint sets are fairly simple geometrically speaking, which is why it did not take very long to do this. The cleaning joint network geometry can take minutes to several hours, or even at the extreme end, a couple of days. So we will proceed now to discretize the model. And now we need to mesh. Great. So first of all, before we get to cleaning the mesh, I'm going to change the external boundaries to rollers along the sides and pins in the corners. Great. Now that our external boundary is fixed, we need to have a look at our mesh. So we'll zoom in a little bit. The amount of mesh that we have far away from the excavations is really not adequate for this model. So I will go back into the mesh setup and increase the number of nodes at all excavations to, say, 250. I will discretize again and mesh again. Great. This mesh is already looking a lot better. We have at least a few triangles of mesh between the blocks between each joint network, far away from the excavation. And as we zoom in to the excavation, we have very small mesh triangles that are fairly uniform, which is a good quality mesh. So we will zoom out and check for mesh quality. And this is great. We have 0 bad elements. With this graded mesh, if we zoom all the way out, you can still see there's some poorer mesh in the corners of the model, but that's sufficiently far away that I'm not very concerned. Now we're ready to compute this model. Alright, so after our model took over 45 minutes to compute, once that's done, we click Interpret to open the model results that are shown here. What first appears is our stage 1, which represents in situ conditions. Because we're using, in this model, gravitational in situ stress field, we can see the slight increase with depth of the sigma 1 due to gravity, where the depth below ground surface at the top of the model is different from the bottom of the model, and so we see that gradient increase in vertical stress. One of the first things I like to do is change my contour options for whatever I'm looking at from the default of auto range in this stage to auto range in all stages. This becomes extremely useful when you're trying to make figures where you want to use the same legend and color scale. So if we step through our model, we go all the way to stage 7, and we'll zoom into the excavation. There's a button at the top to help with that. I like to turn on first the display yielded elements. This displays shear and tensile failure of the mesh material itself. Maybe zoom out a bit so we can see the full extent of that failure. Next, we can display yielded joints. So the red lines show yielded joints, and you can see concentrated around the excavation. And lastly, because we have ground support, in this case just bolts, we can display yielded bolt elements. If we also had a liner, you can display a yielded liner. Great, so now what? How does this look? We've got some yielded elements, so there's some failure going on in the material. Generally, the yielded elements are concentrated near joints, and we have some but not all of the bolt elements yielding. A few other types of contours of results to look at include total displacement, such as what's shown here, and again double check the contour options to have it auto range for all stages. Great. In this case, the auto range all stages aren't really showing all that meaningful results. I'm not exactly sure where our maximum total displacement is located, so in this case it's useful to use a custom range of displacements. 0.06. Great, that shows a little more resolution of our displacement. Now what if we would want to analyze these results a bit more quantitatively? Well, we can do that by querying the boundary for the total displacement or any other type of results in the model. And we do that by going up to Query, Query Boundary, clicking on the excavation that we're wanting to query, and we want to do so on the excavation in this case. And you can see a whole bunch of numbers show up, which represents the total displacement, because those are the contours we're looking at each vertex or node around the boundary. So we can right click on all of this data and we can graph it. And in this case, I'll select all the stages so you can see the development of total displacement from in situ conditions through staging down the excavation and inserting ground support. Great. This is a useful first pass to visualize the data, but it's easy to right-click on the data and copy it and paste it into an Excel window or spreadsheet, or you can just plot in Excel. I prefer just copying the data and pasting in an already somewhat pre-formatted Excel sheet. You can select which one best suits you. I strongly recommend you do this so you can generate composite graphs that show quantitative data from the various models, particularly in this lab assignment. In this data, we can see a huge spike in total displacement, and we can see what XY coordinate this is located at. So XY 27 minus 5. We can go back to our model and inspect where this is happening. And we see at this coordinate, the maximum total displacement is highlighted. As we zoom in, we can see that a sliding wedge of rock that is intersecting the excavation, as well as two cross-cutting joints, and the total displacement of that block is significantly higher than the other side of the joint, suggesting that this block would actually become a sliding wedge in reality if it is insufficiently bolted. So this is a heterogeneous displacement result for this jointed model. I expect you will find similar heterogeneity in your total displacement results around the excavation boundaries, and you'll find it very interesting to compare these types of results to those of your equivalent continuum models where the whole rock mass is modeled with GSI. So that's it for this video. I hope this is helpful for you in your RS2 modeling and particularly relevant for your Lab 12.